Hey, welcome to the video. Today we're going to take a look at how to do binary logistic regression analysis on SPSS. We'll also take a look at some of the assumptions of that test, and we'll take a look at how to report the results of that test. So unlike linear regression analysis, where we have a continuous outcome variable and we're trying to predict a value on that continuous variable using predictor variables, with binary logistic regression analysis, we use predictor variables to try to predict an outcome within a binary categorical variable. And so what we're going to look at today is whether people have an anxiety diagnosis, yes or no. So that's the binary categorical dependent or outcome variable. And we're going to see whether we can predict whether people do or do not have a diagnosis based on their sex and on their age. So 0 in this example is going to stand for no diagnosis of anxiety. 1 is going to stand for diagnosis of anxiety. 0 is going to represent male, 1 is going to represent female, and these are obviously just going to represent the years that the individuals have in age. So if we go over to SPSS, we can start setting this up. So I'm just going to enter anxiety into this top cell. So I'm in variable view, I'm in the name column, I've just put anxiety there. I'm going to put sex here, I'm going to put age here. So that's just naming all the variables. And then I'm going to use the values column to specify what the different levels of these categorical variables are. So if we go here, values next to anxiety, I'll click on this a little bit here. I'm going to enter a 0. So usually when you're doing binary logistic regression analysis, you're going to use a 0 to represent the absence of something and a 1 to represent the presence of something. Obviously, this doesn't work in all cases. For example, if we're looking at sex, that's not really about the presence or absence of anything. Okay, so I've entered a 0 here, and then I'm going to enter no anxiety diagnosis. And then I'll click add. Then I'll do 1, and I'll do anxiety diagnosis. And then I'll click add, then I'll go to OK. So I'll do the same thing for sex. So I'll do 0 equals male, add, and 1 equals female, add, then I'll go to OK. And then lastly, I'm just going to use this measures column to indicate that these two are nominal or categorical variables, so anxiety and sex, and then I'm going to indicate that age is a scale or continuous variable. So once I've done that, I'm going to go to data view. I can see that anxiety, sex, and age have appeared at the top of these 3 columns. And since I have these columns in the same order in my Excel file, it's simply a matter of copying that data and then clicking this top left cell and then pasting it in. And you can see that the numbers that I entered previously using this values tab, when I go to data view, I can see that these have been replaced by the names that I gave to those numbers. If you don't see the names here, just go up to view and then down to value labels and make sure that this is ticked, and that should mean that your numbers are replaced with the names that you gave to those numbers. So a couple of the assumptions of the binary logistic regression analysis are that there is no multicollinearity, so that just means that your predictor variables are not too strongly related to each other, and you also don't want to have outliers. So we can check for outliers as part of the process of running the analysis, but for multicollinearity, we need to check that beforehand. So I'm actually going to sort of do the linear regression procedure to check that. So I'm just going to go to analyze, then down to regression, then across to linear. And then I'm going to move age, so that's, age and sex into the independence box, and anxiety into the dependent box. And then I'm just going to click statistics, and then collinearity diagnostics, then continue, then OK. Okay, so all we're interested in this output is a single value, because most of this isn't really relevant. So all we're going to look at is this coefficients table, and we're going to look at the tolerance column of that table. And what I want to see is that the values here are above 0.1. And since this value is 0.97, that's clearly way above 0.1. So that suggests that this assumption of multicollinearity or the assumption that there is no multicollinearity has been met. So now we can go on to running the binary logistic regression procedure. So if we go to analyze again, and this time, well, same again, down to regression, but this time we go down to binary logistic, and then I'm going to transfer my outcome variable to the dependent box, and I'll transfer the predictor variables to the covariates box. In this example, I'm just using the enter method, so basically that just means that all of the predictor variables are looked at the same time. I'm also going to click this categorical button, and so if you have any categorical variables, you can transfer them over here. And we're just going to select, so that one, sex is selected, that's my only categorical variable. I'm going to click first and then change. And this just means that the SPSS will treat the lowest value as the reference group. So in this case, 0 is allocated to males, 1 is allocated to females. So it's going to use males who have the lower number as the reference group. In this case, it's probably not particularly important to do the step because it's just as intuitive to sort of compare males to females as it is to compare females to males. But if you had a categorical variable where you had where 0 represented the absence of something and 1 represented the presence of something, the result would be more intuitive if you used the group that represented the absence of something as the reference group. So this would be more important, this step, if you had a variable that had represented presence and absence. So all I did was transfer sex over to here. I clicked first, I clicked change. First comes up here, so I'm going to go to continue. Next I'll click on options, and I'm going to click these three here, so classification plots, Hosmer lemma show goodness of fits, case-wise listing of variable of residuals, and confidence intervals. So take that one, then continue. And then we should be okay to keep going, so we go to OK. Okay, so I'm just going to ignore these first couple of things and go down to where it says block 0 beginning block. And so this is how well the model predicts the outcome variable when it doesn't have any of the predictive variables within the model. So in this case, because we had 16 people with a no anxiety diagnosis and we had 14 with an anxiety diagnosis, obviously there are more people in the former group than in the latter group. So SPSS has just predicted that everybody belongs to the former group. So it got 100% correct when it for people in the no anxiety group, and it got 0 correct for the people in the anxiety group. So it got 100% there, 0% there. And so the model, when it was just guessing, basically guessed 53.3% correctly. So we can now go down to the block 1 bit. So this bit is where the model has incorporated the predictive variables into it. And if we look at this, I suppose we could look at the classification table first. So we just looked at it in the context of the model without the predictive variables. So if we compare it to the model with the predictive variables, so classification table again, we can see that the predictions have changed. So it's now, so we have 16 people with no anxiety diagnosis, and the model has predicted that 12 people have no anxiety diagnosis, so that's correct. But it's also predicted that 4 people have an anxiety diagnosis among the people with no anxiety diagnosis. So I've got 75% correct. If we have a look here, so we have 5 plus 9, so 14 people with an anxiety diagnosis. It said that 5 of those people, or it has predicted that 5 of those people have no anxiety diagnosis, and it has predicted correctly that 9 do have an anxiety diagnosis. So it got 64.3% correct. So it gives an overall percentage of correct classifications of 70%. So obviously this is better, the 70%, than the 53.3% when the model didn't contain the predictive variables. But we don't yet know whether that is a significant improvement. So to figure that out, we just need to go down to block 1 method enter, and we can look at this omnibus tests of model coefficients table, and we can see that we have a significant p-value, so it's 0.003. That's below 0.05, so we can conclude based on that the model with the predictor variables was significantly better than the model without the predictor variables. If we also take a look at this model summary table, this gives us an idea of the amount of variation within the outcome variable that the model predicts. So we have a 0.315 here and a 0.421 here. So we basically just have two methods of estimating the amount of variance predicted by the model in the dependent or outcome variable. So to convert these to percentages, we just have to move the decimal place over 2 points or 2 places. So this is 31.5% of the variance, and this is 42.1% of the variance. This one here is a goodness of fit test. So it's just asking, does the model provide a good fit of the data? And what we want to see in this case is that the value, the p-value, is non-significant. So as this number here, 0.506, is above 0.05, this indicates a non-significant effect, and in this case it indicates that the model is a good fit of the data. So I'm just going to actually skip this one. We've had a look at the classification table, and so variables in the equation. So we know that the model overall is able to significantly predict the outcome variable, so anxiety diagnosis in this case. And then we can use these variables in the equation table to look at the individual predictors. So if we take a look first at sex, we can see that sex is positively related to anxiety diagnosis. So we have to remember that we coded male as 0 and female as 1, and we coded no anxiety diagnosis as 0 and anxiety diagnosis as 1. So if we see a positive value here, this actually means that there's an increased likelihood of having an anxiety diagnosis if the individual is female. But if we scroll over to the sig column, we can see that this value here is above 0.05. So there wasn't, so sex didn't make a significant contribution to the model. And so if we move on to age, we can see that age has a negative p-value. So this means that increases in age are associated with decreases in the likelihood of anxiety. And if we go over to the sig value, we can see that in this case we have a sig value below 0.05. And so this indicates that age does make a significant contribution to the model. And in line with this negative value here, we can see that this odds ratio value in the EXPB column, this value is below 1. And this indicates that for every increase in age, there's like a 0.9, is 0.9 less likely that a person will have an anxiety diagnosis. And if we just look at the sex one again, we can see positive value here, and we can see a value above 1 in this case, in this column here. And we can also take a quick look at these columns here. So if we look at the lower and upper limits for the confidence intervals, we can see that for sex, this range contains 1, which is why we have a non-significant value. Basically, we can't rule out the possibility that the probability of having an anxiety diagnosis doesn't change with sex. So it's possible that there's just no relationship between sex and anxiety diagnosis. Conversely, if we look at the age row, we can see that these two values don't contain 1, so they're both below 1, and that's consistent with this significant p-value. Okay, so we keep going down, so I'm going to skip over this. So this one, we just want to take a look at so I'm looking at the case-wise list table, and this will list cases that don't fit the model very well. So in this case, case 12 doesn't fit the model very well. So if we look at like row 12 here, it's saying that this person doesn't really fit with what the model is predicting. And generally speaking, if this z-resid value is above 0.25, you might consider removing that individual from the analysis. In the example that I present soon, I'm just going to say that this person was left in. In the report, you could either say that you removed outliers, or you could explain that the analysis is limited because it contains outliers. Similarly with the multicollinearity assumption, if you did have a problem here, you could consider removing one or more of your predictor variables, because a value below 0.1 here would suggest that maybe some of your predictor variables are kind of measuring the same thing, so it's not really worth having separate predictor variables. So you could consider removing one or more of your predictor variables. Okay, so that's most of the results. So let's take a look at how to report these. So I'm just going to start off by saying that we did a binary logistic regression to examine whether age and sex were associated with the likelihood of having an anxiety diagnosis. So you could use a sentence like that, but obviously you would just need to change the names of the variables to match what it is that you're interested in. And then this is referring to the multicollinearity analysis that we did first. So a preliminary analysis suggested that the assumption of multicollinearity was met. And I've just reported that tolerance value, so that's 0.97. Just to recap, that comes from this coefficients table, and it's the tolerance column there. And then I've referred to the outliers. So an inspection of standardized residual values revealed that there was only one outlier. Then I've just reported the value of that standardized residual, and I've just said that that outlier was kept in the data set. But as I said before, you might consider actually removing outliers from your data set. So that value, I've just reported this value here from the case-wise list table. So that's the assumptions reported. Next, I'm just going to say that the model was statistically significant, suggesting that it could distinguish between those with and without an anxiety diagnosis. So we've got all these stats here, so let's just take a look at where they come from. So we've got chi-squared equals 11.36. And so that comes from, if we go to the block 1 section of the outputs, so that chi-square value is here in the omnibus test of model coefficients, so 11.36. I've just rounded that to 2 decimal places. You can see the degrees of freedom here, so that's what has been reported in brackets here. I've also got n equals 30, so that's just the number of cases or participants. If you're not sure about how many cases or participants you have, you can go up to the case processing summary table, and that gives you your n number. So we've reported the chi-squared, degrees of freedom, n number, and then p equals 0.003. And so then I've just reported, again, this is from the block 1 section, omnibus tests of model coefficients. So it's just the sig value here, 0.003. Okay, next, just explaining how much of the variation within the dependent variable that the model was able to explain. So I've said that the model explained between 31.5%, and I've referred to the Cox and Snell R-square value. So that just comes from the model summary table. So we're still in the block 1 section. So Cox and Snell R-square, 0.315. So I've just moved that decimal place over, the decimal point over, so it's 31.5. So that's what I've reported here. And the same thing for the Nail-Kirk R-square, so 42.1. That comes from the same table, just this column here. Just move that decimal point over 2 places, so it's 42.1. And I've said that the model correctly classified 70% of cases, and that comes from the classification table within the block 1 section. And we can see that the overall percentage of correctly classified cases is 70%. So that's what has been reported. And as shown in table 1, age, but not sex, significantly contributed to the model. So I haven't reported any stats in this sentence. Instead, I've just referred the reader to table 1, because there are lots of stats associated with this sentence. So it's probably easier to report those results within a table. So let's just take a quick look at the table I've produced. So I've just said logistic regression predicting the likelihood of an anxiety diagnosis. So you could use something like this, but obviously you would just replace anxiety diagnosis with the appropriate name for your dependent or outcome variable. And there's lots of, obviously lots of information here, but this is all comes from the variables in the equation table. And I've basically just replicated this table. So I won't go through where all of these numbers come from because, as I say, it's just a replication of this table. So we've got all of the same columns in the same order, the same rows in the same order, and the only difference is I've rounded most of the statistics to 2 decimal places with the exception of p-values, which is sort of the APA style. And just to recap, so age but not sex significantly contributed to the model, and we're just saying that on the basis of these sig values. So sex has a sig value of 0.7072, so that's above 0.05, so there's no significant contribution there, whereas age has a p-value below 0.05, so age does significantly contribute to the model. And I've said, lastly, the age odds ratio of 0.90 suggests that for every increase in age in years, participants were 0.90 times less likely to have an anxiety diagnosis. So we're using less likely because this value is below 1, and that 0.90 also just comes from this table here. So 0.90 is the odds ratio, and we have the same thing here. So that's about all there is to the logistic regression analysis. If you have any questions about anything, just let me know in a comment and I'll get back to you, and thanks very much for watching.